So this is a sigma algebra defined for real numbers. Okay, and so this is a collection of subsets of real numbers. So subsets in this case are like intervals like this between A and B, so A and B, so maybe half open, half closed, both open, and maybe one side is infinity, whatever. So this broad sigma algebra contains all such intervals. Of course, since this is a sigma algebra, all complements of these intervals are also included. And also unions of all those intervals are included in this broad sigma algebra, because otherwise it will not satisfy the axioms of sigma algebra, right? But anyway, just relax here and assume we have some nice sigma algebra behind this scene. Okay, so here's an example of a density function. And so the probability, in this case, if we want to calculate the probability that the random variable is between x1 and x2, we just integrate the density function. Okay, we are assuming that x1 is greater than a and x2 is less than b. Okay, otherwise this density function can be 0, right? So we just ignore all those parts and just consider this case. So this integral will give you the probability. And here's another example. So this is, I would say, the single most important probability distribution you will learn in statistics, which is the normal distribution. So you must memorize this density function. Every year I stress this. I tell students to remember this, but many people don't, unfortunately, and they fail. Anyway, so this mu is a constant. Any real numbers, and this sigma is also a constant, but it's a positive constant. Okay. And maybe you already know that this mu is the average of this random variable x, but we haven't yet defined what average means, and we will do that next week probably. And this sigma, or sigma squared corresponds to the variance of this random variable. Okay. And sigma, of course, represents the standard deviation, which is just the square root of the variance. Okay. In particular, when mu is 0 and sigma is 1, then this is called the standard normal distribution. So this is normal distribution. So normal distribution. Or often we say Gaussian distribution. I think most physics people will prefer this name, Gaussian. Okay, normal distribution or Gaussian distribution. And when, in particular, when mu is 0 and sigma is 1, it's called the standard normal distribution. So just put mu equal to 0 and sigma to 1, you get the density function of this. Okay, so this is the density function of the standard normal distribution. Okay, so this is the so-called bell curve. Okay, it looks like this. So x, the standard normal distribution is symmetric around 0. So this is 0. So symmetric. Okay. Okay. Are you following me? Okay. Yeah, so far we know uniform distribution and the normal distribution. Okay. Let's see. Now move on to our next topic. So sometimes we want to consider a function of random variables. Okay. So let's say x is a random variable. Random variable. And and let's say g is some function from real numbers to real numbers. Okay. Then we may define a new random variable like this. Okay. But remember, random variables are functions. Okay. So x was a function from omega to real numbers. So if we say y is a random variable, it should be also a function from omega to real numbers, right? So does that make sense? So that means y is a random function, measurable function from omega. So y of omega should be g of x of omega. So this is actually a function composition. G after x of omega. Okay. But anyway, in this way we can define a new random variables. Now, suppose we know the density function of x. Okay, let's write this is f(x) of x. Then, what is the density function for the new random variable y? You know, since the density function of x is already defined, and the random variable y is defined in terms of the random variable x, then somehow we should be able to derive this density function from this information, right? So how do we do that? Okay, for simplicity, we assume this function g is a monotone function. Just for the sake of discussion, let's first assume this g is monotone increasing function. Okay, monotone increasing function. By the way, do you know the meaning of this? It means, g is a function from real numbers to real numbers. So if you plot a graph of g, it doesn't decrease. So it doesn't go like this. It is always constant or increasing. Okay, so it does not decrease at any point. It's only increasing, or maybe stay constant at some point. But for simplicity, let's say just increasing, strictly increasing. Yeah, that's easier. So G should look like this. Okay, it will never decrease. It just keep increasing. Sometimes fast, sometimes slow, but it's just increasing. Okay, if that's the case, then the probability that the value of x is between x1 and x2 should be equal to y1, y2, where y1 is equal to g of x1, y2 is equal to g of x2, right? Because, let's say, okay, let's draw this graph again. So g is just increasing. Okay, so this is xy, x1, and this is y1, and this is x2, and this is y2. Okay, so if the random variable x is between this interval, then by definition of y, the random variable is between this region and this interval, right? And their probability should be identical because, okay, how should I write this? Because if we consider this sample space omega, and let's say real numbers, and yet another real numbers. Let's say this is interval, okay, x1, x2. And this x1 corresponds to y1 here. Okay. And the probability that the value of random variable x is between this interval is calculated by this inverse image, right? So this inverse image is this subset. Between this and this. Then now consider, so this interval corresponds to this interval here. This interval here. So if we take, let's take this one. If we take this interval to omega, it will go to here, then go to here. So this interval in y corresponds to exactly the same subset of omega as this interval of x. So that means we are actually looking at the same subset of omega, whether defined through y or defined through x. So these probabilities should be identical, right? So that means uh, if we integrate, x1 to x2, the density function, integrate y1 to y2, the density function of y, these integrals should be the same. Okay? Now, y is g of x. Okay? So let's change the variables here in y. So this will be like y1, y2, fy, gy. And what about this? It will be, this, since y is equal to gy, so this will be dg, dx, and dx. And actually, this y1 should be x1, and this y2 should be x2. We changed the variables here from y to x. Okay, so that means if we consider this x2 as actually a variable instead of a constant, and we differentiate both sides with respect to this, we have, this is just a fundamental theorem of calculus. Fx of x is equal to Fy of, this is g, it's not gy, it should be gx, of course. Gx and dg dx. Okay. So we have this relationship. But what we really want is not this, but we want this. Okay. So again, let's use this one. So we have, okay, since this g is a monotone increasing function, we have its inverse function, right? So we have, let's see. So we have fx of g inverse y. Oh, okay, so this x is replaced with this. Okay. And f of y and dg dx. So what we have here is, so f of y is g inverse y, and we divide by this. Let's see, g dx, but this one is same as dg inverse differentiated by Why?